Hi, thank you, Eduardo. Thanks for the introduction. Hi, everyone. So to avoid taking any more time from the speakers that we are so fortunate to have here today for a live presentation, let's start with the first one. As Eduardo just mentioned, we are very happy to have Andrea Cavallaro as the first speaker for today. Andrea is a professor and the founding director of the Center for Intelligence Sensing at Queen Mary University in London. And he will talk today about multimodal learning for robot perception as the opening talk of this perception-related slot. So, Andrea, if you're ready, you can start sharing your screen. There we go.
Okay.
Okay, perfect. So I will mute.
Can you see? Can you see my screen and can you hear me well?
Yes, perfect. All perfect. Excellent. I'll just mute myself and keep the cameras off so we don't take any of the attention. Okay. So whenever you are ready, please, the floor is yours.
Thank you, Anna, for this introduction, and thank you for the invitation to present our work at the workshop. I'll be covering, as Eduardo mentioned at the beginning, perceptual aspects of robotics. In particular, we'll be looking at how to learn models that can be helpful for a number of robotic applications. And towards the end of the talk, I will describe methods we have developed for collaborations between robots. And I will try to probably open up the floor also for what Guillermo will be talking about after me. Just to give you a visual summary of what we'll be covering, I will first describe a method for multimodal training. In particular, when we want to have a small footprint of an AI model, and we can, however, exploit multiple modalities in training, and we will use only one modality in deployment. And then I will cover the problem of a model that needs to adapt while the robot is deployed because the environmental conditions are changing. And then I will move specifically to audiovisual processing and show some examples of methods we have developed to be able to localize and hear targets that are moving on the ground when a drone is moving. And finally, I will show some examples of multi-robot collaborations for tracking. So let's start with the model I mentioned earlier. So we are interested in training perception models that are capable of using one or multiple modalities for their operation. And the modalities can come from a single robot or from multiple robots or from different parts of the robot. And therefore, there are many design choices there to make. In particular, today we'll focus on the visual and the audio modality. M is our model, and what we are interested in is how to exploit multi-modal learning. And in the context of this presentation, multimodal will relate to information of the same physical phenomenon. It could be a person speaking or some phenomenon that is evolving in space across observation modality so that we can model or explain a particular event. And we will see how we can play with the modalities so that we can extract the best of both modalities. So the first question I would like to ask is, imagine that you are in a situation where either because you want a smaller model or because you haven't available a certain modality at testing time, how can we exploit multiple modalities only in training time, especially when the modality we would not have available at test time is stronger than the modality that we have available at test time. And this is a method we have recently presented at ICAS, the conference in signal processing, and has got as objective that of creating a machine learning model that is trained using more than one modality, but uses only one modality at test time. We do that by using cross-modal translation, meaning that we try and translate the stronger modality into the latent space of the weaker modality. So we have a shared latent space. And here on the right, you see a block diagram, and we'll go in the details of the diagram later on. So we have two layers. The top layer is an autoencoder that works in one modality. The bottom layer is an autoencoder that translates from one modality to the modality of the autoencoder above. And the block you see on the bottom right is actually the classifier we want to use at the end. And the pink blocks are those that are used for the applications, where the other blocks are only used for training time, so to generate the values of the parameters of the model. Let's jump into a few more details on how this approach works. So we have on top an intra-model autoencoder that takes as input a modality, the modality that is only available for training, and generate as output the very same modality. In our case, for example, we imagine we have only video for training. We use the first loss, which is a loss that tries and make the output of the autoencoder be as similar as possible to the input. Then the modality that we want to use, for example, in testing is only audio. And in order to train a classifier that is more successful, more accurate at test time than a classifier that uses audio only in training, then we try to use an intermodal translator, meaning that we have as input audio, and at output of this translator, we will have something that will resemble video. We train this with a loss that takes as input both the output of the intermodal translator and the input of the intramodal autoencoder. Then we need to align those feature representations, and therefore we use a latent feature alignment and the related loss in order to make sure that the information from what we call a stronger modality is distilled into the feature space of the weaker modality. And finally, we have the traditional loss for the classifier that is trained in the traditional way based on annotation. In this case, we have this infrastructure that is used for training, and that at test time, we will use only the bottom part to reach our goal. We have demonstrated this architecture in the context of emotion recognition, and in the ICAS paper by Vandana Rajan, who's a PhD student in the group, and Alessio Brutti from FBK, we have shown that we can outperform the state-of-the-art using this infrastructure, which is particularly helpful, especially if you want to have smaller models to use in your system. A second question I would like to cover in the talk today is different from the previous one. In the previous one, we didn't have a modality in testing. In this second case, we have both modality in testing, but they have varying relative quality. So we start with a model, and then during deployment with the robot, the modalities will have a different quality. How can we exploit the better modality at test time so that the final quality of our perception is better? And also, how can I improve then pre-trained models without using any explicit label? So we have developed with Alessio Brutti from FBK an approach on online cross-model adaptation that adapts the model of one modality using the confidence and the scores of the other modality when the other modality is deemed to be effective. Just one brief visualization there of the model. Theta are the parameters, I and J are the two indices for the modality. I is the modality of the classifier, J here is the modality of the other perceptual input, and we are using the confidence of one perceptual input to improve the performance of the classifier of the other modality over time. And in order to make sure that we are not overfitting or the model diverge, we control this evolution with a KLD regularization. Let's see a visualization of this approach. In the specific case of a camera, in our case here, the validation was on wearable cameras. So we wanted to be able to recognize people in different environments. This is applicable also to robots, either to ground robots or to drones, trying to identify objects or people under different viewpoints and different conditions, especially when those objects are emitting sounds or generating different type of sensor data that can be combined. We used a feature extractor at the beginning and a simple multi-layer perceptron. And you see that this is a hybrid approach that is improving over time the values of the parameters by using the information from the other modality. And then at the end, you have the usual score fusion based on weighting. In this case, we have both modality at test time. And we improve the quality of the recognition by exploiting which modality is deemed to be better at each time instance. So over time, we have varying results in terms of quality of a modality. And because we can estimate the quality of a result, and we are controlling it over time with KLD, we can improve overall the results of recognition through this cross-modal adaptation approach. Now, let's start moving really to robotic platforms. So what I will be covering now is two examples. One example of perception using audio, and then one example of tracking using visual information. This is the first prototype we developed for an auditory drone. So you're all very well familiar with extremely high quality images and videos taken by drones, but we haven't yet heard a lot from drones. And the reason is that the ego noise generated by drones is really very, very high. So this was the first prototype we put together several years ago, trying to characterize the ego noise of the drone and seeing whether we can enable robot-human interaction with drones, whether drones can be used to localize a certain sound source. For example, if it's used for search and rescue applications, in the case of fog on the sea, then can we have an autonomous system that is capable not only of locating where a sound source is, but also of recognizing what the sound source is saying, what the person is saying in case there is a person in distress. So why are we interested in this? Well, we are interested in this because there are a number of applications that could be enabled with audio sensing from drones, and we're trying to find a solution that could be adaptable to any type of drone. So we didn't want to have any particular connections with the architecture, the physical architecture of the drones. We didn't want to use any signal directly from the motors, so that we can have a box which we are developing that can be put on a drone and used as an additional sensor. So this was the prototype of an audiovisual drones we developed, and we collect quite a lot of data. With these data are available, and you see here the evolution of this prototype. And this one on the top right is the latest one we are using. We're using new hardware now and reducing also the size of that microphone array. We have collected also quite some data in a studio to be able really to characterize properly the noise of the drone itself. The use cases for this is situational awareness, filming, of course, human-robot interaction. And what is more relevant for this workshop is robot-to-robot cooperation. So in the first case, we want to have high-quality audio recording. We want to detect the direction of an event and understand what this acoustic event is. We want to be able to provide voice controls to a robot. And finally, we might want to use audio information for robots to be able to localize themselves when they are operating as a swarm, or to be able to understand that there is a drone coming from a certain direction. The dataset I mentioned earlier is available and is called Audiovisual Quadcopter dataset. It has been collected outdoors in a number of controlled conditions. We have collected audio measurements and video measurements, and these are available. If you're interested, just drop me an email. I will send you the link to the dataset. And we have collected information from speakers and also information generated from loudspeakers, so we could reproduce the same capturing conditions. Let me give you an example here, and I apologize. You're going to hear very unpleasant noise now. So if you, in case you have headphones or you have a high loudspeaker, you might want to control it a bit, I will show you what, I will make you listen, what type of sound that drone, when operational, is generating. Lin Wong, who's the colleague who's been working on this project, is in front of the drone. He will say a certain words, so there will be numbers, and I will first show you what type of information is collected from those microphones, and then I will show you the results of our perceptual tools to be able to extract what the person is saying. So I'm going to play now the video. So the sound again will be pretty unpleasant, so control your volume. So could you hear the sound? Yes? Okay. So yes. That is what is, thank you. That is what is recorded. And in the next video, I will show you what is the result of our audio processing pipeline. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Right, so we were able to extract the information that the person was saying without having any information about the position of the person, the position of the microphones, and the type of drones we were using. So the system was completely agnostic of the environmental constraints. The method works by localizing some sources, ranking them, and finding what is a source of interest. So the ego noise from the drones is one of the sources. It's rejected, and we focus only on the person. When we are using together the microphone array and the camera, we need to do some alignment. And this is all information that we have with the dataset we are distributing in order to make sure that when we're using a camera together with a microphone, then we can register the information on the same reference. I will show you now what we can do when, in addition to using just the microphone array, we're using also a camera. And in that case, we might have, we can have multiple people speaking simultaneously. And because we're using the localization from the camera, we can focus on each of these people and extract what they are saying. In this particular video, I will show you first what is the sound collected by the microphones. And then the two people, the one on the left and the one on the right, are saying exactly the same words at the same time. And you will see how the algorithm can extract what a person is saying and what the other person is saying separately. So first, the original noisy audio, and then the So here we were playing just one sound at a time, but in reality, what the system is capable of doing is extracting simultaneously and intelligibly both voices. And so this is the point where we are at, and we are trying to use this through a very, very compact tool. So if you are interested in this, please get in contact. We are really excited about the capabilities of this audio system. Now, before going to the multi-drone approach, I will show you an example which I believe and hopefully introduces Guillermo's presentation here, is one problem we have with drones. So obstacle avoidance is a very important problem. And so a few years ago, we worked on this problem using only the camera embedded in drones, so without any fancy cameras or expensive cameras, and based only on the motion vectors flow, we defined a method that is capable of differentiating the motion that is due to the movement of the drone from the motion of extraneous objects, like in this case, the ball, and use that to control the movement of the drone itself. And again, this is using the 10-30 frames per second camera that is mounted on drones. Nowadays, there are more effective tools that are able to separate the background from the foreground when is needed. But let's go to the last part of this presentation, which is looking at multiple drones communicating with each other. The idea here is to use the perceptual abilities of multiple drones to be able to accomplish a task jointly. And in particular, in this case, we are interested in multiple drones embedded with a camera, communicating with each other, having no control from a centralized control system, and maintaining a certain distance from each other, but also maintaining at the same time at the center of their field of view a certain target of interest. So our objective is to be able to have drones that can collaborate over time, and they can achieve a desired view, maintain at the same time a certain formation without any centralized control. So at the beginning, we tried a number of approaches on this, and it was particularly difficult to compensate for the inertia of the drone, maintaining the formation, and at the same time being able to follow the target. So our objective is to be able to have all drones having the target at the center of the field of view, and through communication enable some of the drones who are losing track of the target to be able to recover that position over time. So these are some examples of early experiments when we were asking the drones to be in a particular position with respect to the target, and then we move on and looked at ways in which we can define algorithms that could enable the drones to follow that target. So this is when you get things wrong. You see that the drones are keeping on trying to follow the target, but failing to do that. And here is again, you see that if you try to be reactive and at the same time to maintain the formation, your objectives are too constraining in your behavior, and it's difficult to succeed in maintaining it for a long time. So the cones you see there is representing the field of view of the camera. The points you see there are, in the case of this early work, the desired position with respect to the target. Then the most recent work we have in this area is not considering any desired position with respect to the target, but simply considering the target position within the frame of view of the camera in a certain desired location. So as you see here, our drones, by communicating among each other without any centralized control unit, are trying to maintain the target at the center of the field of view, trying to maintain the relative position with respect to the other drones in order to have the target at the center of the field of view. So the drones are generating a consensus on the velocity they have to have. So they express their desired velocity, and then they have a round of consensus among their teammates, and then they move based on this reached consensus. And you will see that even in some cases when the drones get outside the field of view, then it can be recovered because drones are communicating with each other their relative position. And in this case, the camera is fixed on the drone. We're not using any pan tilt or zoom type of system. And now we have recently got a new grant to find what are the best way for this swarm or robot to be able to communicate effectively with each other under varying conditions. These results are under ideal conditions. This new project will be under realistic conditions with real drone swarms. So as a summary, we have been looking at models that are using multimodal data to improve the accuracy of the perception. We looked at audiovisual processing, how we can start from audio processing on drones, how to enhance that with visual processing, and how to coordinate the two streams. And finally, how robots can collaborate with each other when they have the same goal, but no control, centralized control unit. In the first case, it was the uni-modal tool that was trained with multiple modalities. In the second case, it was the adaptation on test time. And finally, we looked at drones collaborating with each other. This work has been done by a number of people in the group, Vandana, Alessio, Lynn, Ricardo, Michael, and Fabio, which I thank very much. And I thank you also very much for your attention.
Okay, thanks a lot for the talk, Andrea. We see some virtual claps in the audience. So maybe we can now have a few minutes for discussion before we move to the next speaker, which you already nicely introduced. You already mentioned Guillermo. So before switching to his talk, any question from the audience? You can, for example, raise your hand and then unmute your mic. Eduardo has the hand raised, so please go ahead.
So as you know, I'm more from the control side of view, so this question might be something maybe trivial from the learning part, but I was wondering, when you had the two modalities and you were learning and feeding the confidence of one sensor into the learning part of the other sensor. So my question here is that, considering that technically the two measurements of the two sensor measurements are acquired at the same time, so how can you feed the confidence of one measurement without first processing that measurement that at the same time requires the confidence of the other measurement? I'm not sure if I'm making sense here. So I wanted to know more or less how does that work?
I see what you mean, and it's something probably I should have clarified better. So the idea there is to take a decision with the pipeline as things are going, but using these streams to improve the models under the assumption that if for example, the drone in our case, or the wearable camera goes from an area, imagine that you go from indoor to outdoors. The sound conditions are changing a lot.
Yes.
And maybe if someone is dressed in a certain way, the visibility conditions are not changing. So in that case, you will learn that you have a new environment because one of the modality drops its quality. But because the first modality maintains a certain quality, then we can use the label. In our case, the label would be the identity of the object. That identity of the object can be used to keep on improving the model of the other modality, so that at the next time instance, they will be able to better predict the identity of the object. So the improvement will not have an impact at the sampling time for which that is recovered, but it will be for future times, under the assumption that there is continuity of conditions, and it's not just a burst that happens for a few milliseconds.
Okay.
So the idea will be that the performance will drop and then rise again.
So it's more a temporal thing rather than just a punctual classification.
That's correct.
So, okay.
That's
okay.
correct.
Okay.
Yes.
Thank you.
Okay, thanks for the clarifications, Andrea. I think George also has a question. Please, George, go ahead.
Yes, quick question. Thank you, Andrea. So in that last example that you gave for the target tracking,
yes.
Are you considering extending that algorithm to tracking multiple targets, and especially if those targets themselves are, let's say, a flock of agents or a multi-agent system?
That would be a very interesting extension, because then you would have also perhaps the choice of how to split the team. So if you have a sufficiently large number of drones, maybe you start with an exceedingly large number of drones with respect to task at the beginning when all the targets are together, and then you will need to have some assignment algorithms that, in addition to assigning targets to identities, you will also have to assign drones to targets. We haven't yet worked on that, but that's certainly a very interesting problem. We have in the lab a substantial experience in multi-target tracking and multi-camera tracking, and this is certainly an area of great interest.
Okay, thanks.
Thanks again, Andrea, for the questions. Maybe we can take a last quick one from Guillermo before we switch to his talk. Go ahead, please, Guillermo.
Yes, thank you very much. Andrea, I have a question about the first question that you point out, that is when you have two sources and how would you use or decide to use one instead of the other. So the part that is a bit counterintuitive to me is that the senses we have kind of, they don't overlap too much. So I guess in a mathematical way, it would be that it would be optimal to choose one sensor and not choose the other. So in a sense, if you want to have the redundancy and robustness, you need to kind of know when the sensors overlap in the goal that they want to have, and how much can you use one sensor and not the other one. I mean, when you have vision and audio, and they are two different sensors and they want to pursue the same goal, my feeling is that the animals will use just one, and when you are impaired with that sensor, you feel like you lost completely your senses, and it takes a lot of time to use the other sensor for the same goal. So how is that robustness enforced in your system?
So that comes from the training data. So what we are trying to do here is to start from the assumption that we will have a single modality at test time. Now, we don't have two modalities. We have one single modality. We can use a latent space trained only on that modality, or we can use a latent space that has been trained on that very same task using two modalities. The one that is not available at test time is more accurate than the one that is available at test time. And through that block in the middle, the latent feature alignment, we are distilling the knowledge from the stronger modality to the weaker modality. So the bottom intermodal translator here is going from the modality that is available at test time to the modality that is not available at the test time. And so there is a loss between the output here and the output there. So we are trying to transform that modality into the one that is not available, so that the latent space that is in here, I assume you're seeing my mouse.
Yes.
So the latent modality that is here is not trained only in a traditional way with an autoencoder, but is trained also by taking the co-occurrence of information for that event that is visible only in the other modality, and shaping the weaker modality in such a way that it adapts to the information that wouldn't be available if the training was done only with one modality. So I take your point that is counterintuitive if you think at it as a traditional multimodal approach, but that's one of the reasons why I'm so happy with this type of work, because it tries to make the most of the learning process in machine learning, where you try and see information that is not evident from the pair input data and label in one modality, and see how you can modify the latent space. So here is not just the features, it's the way the latent space here is built that is worked and modified with the information from the stronger modality.
Okay, I guess then the follow-up question, just a short one, is when is it possible to always reshape the latent space so that there is overlap between the two sensors? When can you always make this translation? I mean, is it always possible?
So we validated this in the context of affect recognition. So we have used standard affect recognition data sets. And we showed that in the case of those data sets, we can outperform any unimodal classifier that is not using that information. You probably would have a hard time if you're trying to do transfer learning on this, because it might be more difficult to modify the space on a very different task. But we haven't looked at that yet. So, and certainly looking at it from a more mathematical viewpoint could be particularly interesting, and I'll be very happy to have a chat with you if you're interested in this.
Thank you very much.
Okay,